Hello, everyone. Today I'm going to present a comparative theoretical study on access risk bounds of deep neural network in the Rademacher complexity versus neural tangent kernel frameworks. The motivation for this study, because the generalization is still a challenge for deep neural network. Specifically of interest is access risk for the purpose of quantify how far a learned predictor based on the sample data from the optimal predictor for the population. There were extensions of classical Rademacher complexity-based approach in terms of bounding the excess error with constraints and with specific limitations. What I wanted to do is to explore an alternative approach based on modern machine learning theory, specifically in this study based on the NTK regime. I want to derive access bounds based on NTK, and then based on that, in reverse, derive sample size requirement, which could be of value for practitioner. Agenda for today's presentation, I'll go through quickly the backgrounds. What is the classical generalization, Rademacher complexity, the DNN-specific challenges, and then what is NTK. And then I'll describe a study already done based on the Rademacher-based complexity-based access risk bound, and then the sample size derived based on that. And then the main purpose of the study is to explore the NTK-based access risk bounds, and then the sample size estimation based on that bound. At the end, I will quickly go through a quick comparison of the two approaches and the limitations as well as potential future work. Background for the generalization, we learned in our class the generalization error, which measures for any hypothesis, what is the population loss for that hypothesis, minus the sample loss for the same hypothesis. Access risk can be defined further to measure how far a predictor is from the optimal predictor of the population in the same class. All these are measured on the population level. So specific formally, it's the loss of a hypothesis minus the population loss. Both are population loss minus the population loss for the population optimum hypothesis, which is noted as H star. And particularly of interest in practice is the excess error bound, specifically for the optimal hypothesis based on the sample data, what we call it empirical risk minimizer, and notation H hat. An important feature is if we could bound the generalization error, then we could decompose the excess risk into three components. Two of them actually are generalization error, just based on different hypotheses, and then the middle one showing on the screen is the optimization gap, which by definition, the optimization gap is actually less than or equals to 0. So for the conservative bounding of excess risk, we could ignore the middle term, the second component, and then the first and third components can be derived just based on doubling the generalization error bounds. So that's the main framework of the study. And Rademacher complexity, as we learned in class, I won't go through the definition in details. And then the generalization error bounds for a loss function between 0 and 1, we derived the uniform bound, the generalization bound. And then, as mentioned earlier, based on that, we can derive the excess risk bounds with being less than epsilon with high probability. The specific challenge for deep neural network mainly came from because DNN is characterized by multiple layers with nonlinear transformation. And because of that, uncontrolled Rademacher complexity may scale poorly and very quickly with accumulation effect, especially because many DNN has millions of parameters. So that would lead to vacuous bounds. One solution is certainly we could use norm-based improvement, bounding them, and in which case Rademacher complexity could be useful, which we'll cover in the next couple of pages. A quick refresh of NTK regime. That's the fundamental assumption is a very wide or infinite network, which can be approximated, which can essentially follow a linearized dynamics during the DNN training. Because of that, DNN training can be approximated as a kernel machine with a kernel defined on the screen. And then the training can be analyzed as a kernel ridge regression. Here we use ridge regression to be more general. Essentially just include a regularizer lambda. This would enable the analysis for DNN in the RKHS space for the risk for the excess risk analysis. So as mentioned earlier, there were work before already. The example here is by Golovich in 2018, which improved the Rademacher complexity-based bounds, but follow the same approach. We first bound the Rademacher complexity, and then that contributed to the bound of generalization error, which then can be used to derive the bound for excess error, defined in the context of excess error is less than a specific target epsilon with high probability. And then in reverse, so here on the screen we can here on the screen we can show the final bounds, which is actually defined based on the constraint shown earlier in terms of the input x, which reflect in the R2. Sometimes there's a constant, and then this component is actually the product of the norm bound for the weight for the parameters of interest. On top of that, this term is called stable rank, which measures the sum of the squared ratio between Frobenius norm and the spectral norm, and then square root the overall summation. And then there's certainly this generalization term of 6 times log 2 over delta and divided by 2n. So this is actually excess error bound for the Rademacher complexity-based approach. Based on that, we can derive the sample size. So it requires the n larger than it's actually a simplification because just for convenience of practice, it's sufficient bound but not the tighter bound. So it requires the sample size should be larger than either of those two quantities. And then we come to the NTK. So NTK follows assumptions as we learned in class. One is the NTK is linearizable with lazy regime. Essentially, it's referring to a very small learning rate. And then the fundamental concept is the kernel, including empirical kernel and the general definition of a population kernel. The idea is the target or the projection of the target will be bounded also in the RKHS space. As mentioned earlier, by all these assumptions, the DNN training can be analyzed as a kernel ridge regression with regularizer lambda. And on top of that, the general assumption is the underlying data, the true data for the population follows a model shown here, y being the response, and then a function of xi. Here we use f star. This is a function in the RKHS space, and with the noise following sub-Gaussian distribution with the expectation equals to 0 given x, and then the variance of sigma square. So the excess risk, the NTK excess risk bound setup. The idea is, given all those approximations we mentioned earlier and assumptions, it is sufficient to analyze that the kernel ridge regression in the RKHS framework, as shown on the screen. That's the formal definition of the KRR. And then the excess risk, there's a property called excess risk identity, where the essentially the squared error of the empirical DRM versus the optimal, the predictor, the squared error of that is essentially equivalent to the excess risk. And this will be helpful for the further derivation later. And then we have this general bias variance decomposition for this expected squared error, and it can be bounded by the on the right-hand side as 2 times lambda, and then defined by the norm of the function, the optimal function for the population in the kernel space. And the second term of this bound right-hand side is actually a trace of a gram matrix, trace of a matrix structure derived by the gram matrix. So because of this setup, an important aspect of the NTK analysis is to analyze the eigenvalues of the gram matrix, as shown here. So this can simplify the second term in the equation above for the bias variance decomposition. Different from the Rademacher complexity, the NTK excess risk bound follows 2 steps. The first step is to bound the expectation we mentioned earlier, here with some simplification, building in the some assumptions of the bound for the different components, and that can be actually further optimized by choosing the optimal lambda, as shown on the second line here. And then the second step is actually based on that expectation bound. We can then derive high probability bound for the remember the identity we mentioned earlier. So this is essentially bounding the excess risk, but we need the context of with high probability to control the excess risk is less than a specific target lambda. So the sample size then can be derived based on the high probability bounds. So as shown at the bottom of this page, it's similar, like it's 2 component. So we require the sample size to be at least as the higher of one of the 2 components. And then a quick comparison of the 2 approaches. So Rademacher complexity bounds actually depends on parameter norms, as mentioned in the assumptions. We call it B for the parameter norm bounds, and then the stable rank we mentioned earlier. On the other hand, NTK depends on mainly because it depends on the RKHS space properties. Rademacher complexity is distribution free, so it's non-parametric, but it's more conservative. On the other hand, NTK has its own requirements because the underlying assumption is infinite width or very wide regime. However, in some situations, which approach dominates really depends on the architecture and the target alignment. For example, NTK may yield tighter bounds if the optimal population predictor aligns well with the NTK RKHS space. There's quite some limitations and potential future work. One is all the NTK assumptions, linearization assumptions, was based on infinite or very wide network. So if in practice, many times that wide network may not be very appropriate. So there could be work further down to assess, in the case of finite width, what kind of corrections could help also enable the analysis we did in this study. Another potential future work is really to RC bound may be loose. As we mentioned, it's non-parametric conservative. It will be loose without margin or localization. So that's another area could be further studied. We present the 2 approaches, but as I said earlier, they are really in a different framework. So NTK is really focusing on the RKHS space with its own bound. So there's opportunity we could link those bounds, and that will help us eventually for the future goal. Hopefully we can define the efficiency of the 2 approaches in terms of a ratio of the sample size between the 2 under the comparable assumptions. So with that, thank you for your time, and I'm open to questions.